Okay, let us continue to see the relation between the tractive effort and tractive resistance. Okay, in figure A here, the top gear performance, which is previously plotted as a difference in power, is shown as a balance of forces. It will be seen that the driving force curve is similar in shape to the engine torque curve. So driving force punya curve and the engine torque curve is similar. The peak of tractive effort curve occurs at road speed controlled by overall gear ratio and effective diameter of the road wheel. So the difference between the effort and resistive curves, so this is the difference between the tractive effort and the resistive curves, represent the force available for acceleration. So this will be, if this is the maximum, this will be the maximum acceleration. Other than that, will be the just normal acceleration punya availability. And figure B here, it shows the effect of tractive effort curve of lowering the gear ratio. So in this case, the bottom gear ratio is 4:1. Is used to amplify the tractive effort sufficiently to meet the hill climbing. So during the hill climbing, the maximum tractive effort required is like this, and when you have the gear ratio, the tractive effort curve will be like this. So this is where, here is where the acceleration needed. It's higher acceleration needed to climb the acceleration is not so big, but the most important is the power to climb, or the, and in this figure also, gradually engagement action, the clutch must be used to provide tractive effort built sufficient to move off the vehicle on the steep hill, represented by the graph. Once the clutch is fully engaged, the engine is operating in the region of maximum torque. So during the maximum torque, a small acceleration is possible, because when you climb a hill, the acceleration is not important. The most important thing is to move the car, and this assumes that the engine speed does not drop too low. So the bottom gear ratio is calculated by dividing the maximum effort required by the maximum effort available in top gear. So before you use to search for bottom gear ratio, you will have to search for the top gear. So the previous one we talk about top gear ratio, and the intermediate gears 3, 4. For example, the top one is 4, the bottom one is 1, gear 1, and the intermediate gears will be the second gear and third gear. Having set the top and bottom gear ratio, the intermediate ratio are then inserted so that they form a geometry progression, or GP. And this means that all the individual ratio advance by a common ratio. For example, the top and bottom overall is bottom is 4:1, top is 16:1 respectively, and then the set of ratio 3 and 4 speed gearbox. Kalau 3 speed, we have 4 and 16, top and bottom. And for speed, we have top and 16 also. So intermediate will be 8 for third speed gearbox, and for 4-speed gearbox the intermediate will be 6.35 and 10. So this common ratio will be 2 and 1.59. To obtain the optimum speed and acceleration performance, the engine should be operated in the speed range between the limit of maximum torque and maximum power, between these. So the wider this operating range, the smaller is the number of ratios required, and to bridge the gap between top and bottom. And most modern car engines have a narrow range, so the gearbox fitted in the conjunction of these engines normally have at least 4 gear ratios. And since most cars are under geared, it is common practice to have a extra gear called the 5th gear, that will be the over gear, to offset some of the drawbacks associated with the under gear condition. Normally this gear is an overdrive because it has a ratio that steep up the speed. As a result, the output shaft is faster than the engine rotation. The output shaft rotation is faster than the engine shaft rotation. Okay, so that's all for gear ratio. I've given you some of the example of calculating the gear ratios. Please look up the exercises so that you understand how the gear ratios can be calculated. Okay, that's all.